In the same way, we will just go for calculating the capacitance on the transmission line. First, we will just imagine how the capacitance is forming on the transmission network. We know very well the transmission network, we are having a 3-conductor if it is a 3-phase system. Suppose in rare case if it is a single-phase system, it may have 2 conductors. Also, we know the condition of the capacitance formation. 2 electrodes should be there, and these 2 electrodes should be separated with a dielectric media. And here in the transmission network, air will act as a dielectric media, and those 2 conductors act as electrodes. So this forms a capacitance effect on the transmission network. Not only in this among the conductors, also the capacitance effect forms between the earth to the conductor. So there are 2 cases are there. Just slowly one by one we will go. So now the transmission line capacitance formation depends upon material, size, position, spacing among the conductors. The same thing what we have seen for the same inductance. The capacitance C, we can call it as, we can say the charge by potential difference, as like in your inductance we have seen for magnetic flux linkage by current. How to define the electrical potential? It's a potential difference. We need a 2 point, and if we just simply consider a conductor, then we have to consider the another point at the infinity point somewhere else where your potential is 0. That means a neutral plane we have to consider. The earth potential, electric potential at a point due to a charge is the work done in bringing a unit positive charge from the infinity to that point. E equal to, we can call it, we can say QA by 2 pi x epsilon naught. Actually this is the epsilon, and epsilon naught, epsilon r will be there, and simply this epsilon r equal to 1. This is nothing but permittivity. So if we just see the capacitance equation or derivation, we can simply compare with the inductance calculation, and simply we can able to remember how to calculate the capacitance equation. Now again we will consider a small conductor, and here we are not going to consider any internal external like that, because the conductor formation is only between the 2 conductors, and so we have to consider the limits while we are going for integrating from distance r to infinity. There is no any consideration of integral limits for 0 to r, because it's a electrode. Between the 2 electrodes there will be a dielectric media and the capacitance forms. So now if you see here, conductor A we are considering, and its radius is r, and QA charge is there, and the 0 potential is somewhere else at the infinity, and we are considering a point P at some distance of x meters, and at point P what is the electric potential? If you see, EA on conductor A equal to integral of r to infinity QA by 2 pi x epsilon naught dx. This is the equation for that conductor from distance r to infinity. This is because of single conductor. Suppose if we go for number of conductor as like a 3-phase double circuit line, we may have 6 conductors, and in order to calculate the capacitance or potential, electric potential at conductor A, then we have to consider the remaining neighbor conductors also, because those charges also that disturbs the charge, net charge of your conductor A. So now how to make that one? So as simply here we know that we are having the limits from r to infinity. In the same way for conductor B, C, D, E, F, we can say that EAB, that is electric potential on conductor A because of charge QB is equal to integral D1 to infinity, that's D1 is the distance between conductor A and B, QB by 2 pi x epsilon naught dx. In case of EAC, that is electric potential on conductor A because of charge QC is equal to integral of dt to infinity QC by 2 pi x epsilon naught dx, and so on. So for remaining conductors for EAF like that, if you say, we can just go ahead with that one. Finally, if we sum up all the charge, all the potential, then we will get the net potential of that one. Now, what are all the things we have to go through? Capacitance formation or calculation for single phase single circuit line, capacitance calculation for single phase double circuit line, capacitance calculation for three phase single circuit, capacitance calculation for three phase double circuit. In this again double circuit we will try afterwards, just we are going to see for single phase only. And in this case, within the bracket, if you see, we are having without and with earth effect. What is the meaning of this without and with earth effect? As I told, the capacitance formation is not only among the conductors, also between the earth to your conductors. Now if we consider that earth also within this, then what will be the net capacitance effect without considering the earth effect? So these two are a separate calculation. Again, for all the cases we can able to go for with, without, like that. Now we will go for capacitance calculation for single phase transmission line. As I said that there are more similarities are there, as like the inductance, here also capacitance derivation will be there, so we no need to go for much on explaining these things, so directly I will go. So consider again the same single phase single circuit line. We are having two conductors A, B, and the charge flowing on conductor A may be plus Q and charge on B conductor is minus Q, or it may be a QA, QB like that, and distance between the two conductors is d meters. And we know very well, as like in inductance equation also, we say that IA plus IB equal to 0, or otherwise IA equal to minus IB. In the same way here we can say QB equal to minus QA, or QA equal to minus QB. So to find capacitance with respect to infinite neutral plane, potential EA at conductor A is EAA plus EAB. So again I no need to explain about EAA and EAB. This is because of charge QA and QB, and if we write the equation, this will become from the limits from R to infinity, and because of charge QA, and for here the limits are d to infinity, and because of charge QB. So now if we solve this equation, the same form here, the infinity terms we can take it outside, and simply we will get QB plus QC. This term will be vanished, this will become 0, and in place of QB we can able to substitute QA, and if we substitute simply again we can commonly take outside, then finally we will get the electrical potential on conductor A equal to QA by 2 pi epsilon naught ln d by R. So now again further we can able to reduce the equation on substituting the value of E naught, that is epsilon naught. Epsilon naught equal to 8.854 into 10 to the power minus 12. On substituting this equation, further we can able to reduce the equation. Otherwise simply we can keep it in terms of epsilon naught itself. This is for conductor A with infinite neutral plane. The same way, if we consider or to calculate the capacitance for conductor B to infinite neutral plane, then we will get EB equal to minus QA by 2 pi epsilon naught ln d by r. So the minus QA, or otherwise you can call it as simply positive QB. Now if you want to calculate the capacitance effect among the two conductors, then we have to take the potential difference among the two conductors. The potential difference between the two conductors VAB, or it may be EAB, equal to, instead of EAB here we consider VAB, because in earlier slide we mentioned EAB. That's why here we are putting here VAB, potential difference. VAB equal to EA minus EB, and if we substitute, finally we will get the equation QA by pi epsilon naught ln d by r. In order to calculate the capacitance, we are having the equation QA by VAB, and on substituting the value we will get CAB equal to pi epsilon naught by ln d by r. In the way, we can also able to calculate the CNN or Cn. So this is somewhat like between the two conductor there will be a neutral point, because one conductor is the phase conductor, another one is the neutral conductor. So positive Q, negative Q is there. So there will be a zero potential will be there. Zero charge will be there because of plus Q and negative Q. So there we can able to calculate the capacitance from A to N, B to N. So that equation is this one, as what we derived earlier in the last session. This case, both are same one. Now it's for three-phase transmission line. Here also we have to go for a symmetrical spacing as well as unsymmetrical spacing. Now again consider three conductors ABC of radius r meters and distances d on all, d1 equal to d2 equal to d3 equal to simply d. Again here electrical potential EA equal to EAA plus EAB plus EAC, and on substituting these values we will get this equation. If we solve this equation, finally we are getting EA equal to QA by 2 pi epsilon naught ln d by r. This d how we are getting means on substituting the value of d1 d2. Okay, so this d2 is here, d2 d3 is there, both are same distance. We can represent, instead of d1 d2 d3 we can simply say d here and also here d. If we solve, then we will get the equation in terms of ln d by r. So now we are having EA equal to QA 2 pi epsilon naught ln d by r, and in the same way we can able to calculate the capacitance on conductor A equal to 2 pi epsilon naught by ln d by r. This is the final expression. Again this equation you can able to compare with your single phase equation, that is 2 pi epsilon naught divided by ln d by r. So now this is for symmetrical case, and for unsymmetrical case we will just move on to this case. And in this slide, if you say, we have to say that QA plus QB plus QC equal to 0 obviously, and the distance among the conductors are not same, so we can't able to equate all. So since it's an unsymmetrical case, we have to go for transpositioning the conductors. Again, as like in inductance, we have to calculate the electric potential for session 1, session 2, session 3, and finally we have to take the average of 3. For EA1, this is the format, and for EA2 for session 2, this is the format, and for EA3 this is the format. On solving this equation, here we are representing for first EA1. On solving this, we will get EA equal to 1 by 2 pi epsilon naught into 0. This 0 is for infinity term, that is QA plus QB plus QC equal to 0. And the remaining terms we are having QA, QB, QC, and we are keeping as it is in this equation. In the same way for EA2, EA3 we are calculating on taking the average of all the three sessions. EA equal to EA1 plus EA2 plus EA3 by 3, we will get the final equation EA equal to QA by 2 pi epsilon naught ln cubed root of d1 d2 d3 by R. Now from this electrical potential on conductor A, we can calculate the capacitance on conductor A equal to 2 pi epsilon naught by ln cubed root of d1 d2 d3 by R. So now we can able to compare these results to your inductance. For single phase single circuit, three phase single circuit symmetrical, as well as for unsymmetrical. On all the cases, if you say the natural logarithmic terms in numerator, either it may be a distance among the conductors, and for unsymmetrical case it's a cubed root of d1 d2 d3, that is GMD. And in case of denominator on your inductance calculation, it's simply R dash, that is effective radius of the conductor. That is because of skin effect there in inductance case. In capacitance case, we are simply having the radius of the conductor. So here in the denominator only, there is a variation in your inductance as well as in capacitance in logarithmic terms, natural logarithmic term. Because here in capacitance calculation, we will not say any effective radius or like that, because there that effective radius is because of magnetic flux linkage, because of skin effect. Here there is no any skin effect. When we are talking about capacitance, we are only considering the outermost part of the conductor from R to infinity. So it's purely a electrostatic field, but that one is because of electromagnetic field.